Hi everyone, welcome once more to this channel, Best Science Brain YouTube channel. Today we are going to take a chemistry content, and the topic we are going to have today is from physical chemistry for first year students. The topic we're going to have is chemical equilibrium. Chemical equilibrium. So if you are not subscribed to the channel and the video is playing, locate the subscription button either under the video or above the video in your YouTube and tap on it only once and get subscribed to the channel. Subscribe, you'll be seeing a video from time to time. Whenever we post a video, you get the notifications. So today we're going to look at chemical equilibrium. Before we go to equilibrium, the first we want to define is what is meant by reversible reaction, because reversible reaction occurs chemical equilibrium will only occur in a reaction that is reversible. So in chemistry, reversible reaction this is a reaction which occurs in two directions simultaneously under favorable conditions. Any reaction that occurs at the same time in both directions under favorable conditions is called a reversible reaction. For instance, let's say we have A molecule plus B molecule giving us 2AB molecule. Now, what signs show that this reaction is reversible? When we see two arrows pointing in opposite direction. So this is the reversibility sign in chemistry. So what it means is that A and B react to give you 2AB. At the same time, AB decompose to give you A molecule and B molecule. The first arrow is called the forward reaction, while the other one is called the reverse or backward reaction. So this reaction is reversible reaction. So a reaction that takes place in two directions at the same time under favorable conditions is known as a reversible reaction. It's worthy to know that, let's look at these examples we have on the board. Let's call this one reaction A, B, and then let's call this one reaction C. So let's look at the three reactions and see whether they are exactly the same thing. So A, B, C. Are the three reactions all reversible reactions? Yes. The three reactions are all reversible reactions A, B, and C, because the reversibility sign is in three of them. But let's look at B and C. Starting with B. If you look at B, you see that this arrow is longer than this arrow. What it means is that the rate of forward, rate implies, or rate is synonymous with speed. This R means rate, F means forward. Rate of forward reaction, rate of reverse reaction. The rate of forward reaction is greater than the rate of reverse. What it means is that A and B are reacting faster to give us AB than AB decomposing to give us A and B. That means you're getting more of AB than you're getting A and B. So rate of forward is faster than the rate of backward. Look at the second example. This is the forward reaction rate. This is the reverse reaction rate. In this second example, you see that the reverse reaction is longer than the forward. In this one, now say the rate of reverse is faster than the rate of forward. What does it mean? It means you are producing more of A and B than you're getting AB. So A and B decomposing faster to give you AB than AB react to give you A and B. AB. I repeat myself. This reaction means reverse being faster means the backward is occurring faster than the forward. So you're getting more of the reactant than you have on the product side. You look at the reaction A. In A part, you see that the rate of forward, the two arrows appear to be equal. That means the rate of forward is equal to the rate of reverse. So that A condition whereby the rate of forward is equal to the rate of reverse is called dynamic equilibrium. They repeat this process again. In the B example, the first arrow is longer than the reverse arrow. What it means is that the reactants are reacting to give you the product more than the product is decomposing to give you back the reactant. That means the rate of forward you had and the rate of backward. I mean, you have more product than reactants in this second example. In the third example, you see that the rate of reverse is longer or faster than the rate of forward. What it means is that you have more reactants and lesser products. But in the first example, it appears that the two rates are equal. That is what is meant by dynamic equilibrium in a reversible reaction. So we'll now go over to dynamic equilibrium. As we defined, dynamic equilibrium occurs in a reversible reaction when the rate of forward reaction is equal to the rate of reverse reaction. So we say this is a condition in a reversible reaction when the rate of forward, that's RF, reaction is equal to the rate of reverse reaction, R. So what are the conditions for dynamic equilibrium to be established in a reversible reaction? There are 5 conditions. The first is that the rate of forward reaction must be equal to the rate of reverse reaction. That means both the forward reaction and the reverse must occur at the same speed or the same velocity. Number 2 condition says the concentration of the system must be constant. The third condition says the change in Gibbs, GIBB, Gibbs free energy, delta G, G means Gibbs free energy, must be 0. So Gibbs free energy is the energy required to perform work in a thermodynamic system developed by a man called Ernest Gibbs. So the Gibbs energy, given by the formula delta G from thermodynamics is equal to delta H minus T delta S, where delta G is Gibbs change in Gibbs energy, delta H is the enthalpy, change in enthalpy or change in heat of reaction, T is the temperature in Kelvin, and then delta S is change in entropy. So if this is 0, that means we now have 0 equal to delta H minus T delta S. And that means delta H now becomes equal to T delta S, crossing this one over. So when delta G is 0, this condition means for this to be 0, that means the change in enthalpy or heat of reaction will be equal to the product of the temperature in Kelvin times the change in entropy. So that means when we have this equal to this or this equal to 0, that means the reaction is at equilibrium. The fourth condition is that the reaction must occur in a closed system. What do I mean by a closed system? Let's look at this reaction, for instance. When you heat calcium carbonate, it breaks down to give you calcium oxide and CO2. So if this reaction is performed in an open vessel, where you are heating the calcium carbonate, this reaction can never attain equilibrium because one of the products is gaseous. It will be escaping from the system. So you cannot have equilibrium in this condition. But if the vessel is covered with a tight lid, covered very well, to prevent the CO2 from going out, then this reaction can now attain equilibrium. You see that? So as long as one of the reactants or one of the products is volatile, it can escape from the container. So if you want to maintain equilibrium, that means the reaction will now be performed in a closed container so that that volatile or gaseous reactant or product will not escape. So that's what we mean by a closed system, a system whereby matter remains constant. That is a closed system. Then the fifth condition for you to for us to have dynamic is that number 5 is that the reaction quotient, which is my right as Q, must be equal to the equilibrium constant K. So we're going to elaborate on this as we go on. This number 5, reaction quotient must be equal to equilibrium constant Q. So next, look at a very important factor called the equilibrium constant, whose symbol is K. So what is equilibrium constant? We say this is the ratio of the concentration of products raised to their stoichiometric moles to those of reactants in an equilibrium reaction. I repeat myself. This is the ratio of the concentration of products raised to their stoichiometric moles to those of the reactants in an equilibrium reaction. Now, for instance, we have this reaction A, small a, big A, small b, big B, giving us small c, big letter C, and small d, capital letter D. Where capital A and B are the reactants, capital C and D are the products. Then small a and small b, we'll call this one the number of moles. Those numbers used to balance the equation, which normally call the stoichiometric number of moles, which could be whole numbers like 1, 2, 3, and so on. Small d and small d also number of moles on the product side. Now, if I want to write the symbol K, the equilibrium constant for this reaction, and now put C in a square bracket. That square bracket means concentration. So in chemistry, when we have a square bracket, it means concentration. Now, if I put a substance inside it like C, it means concentration of C, as you have it there, raised to its number of moles, which is C. Then the other product, D, in square bracket, raised to its number of moles, which is D. All over. That of the reactants, you have A, raised to the number of moles of A, which is small a, multiplied by the that of B, raised to its number of moles, which is small b. So this represents a hypothetical example of equilibrium constant, how to write it. So it says the ratio of the concentration of the products raised to the number of moles to those of the reactants raised to their own number of moles. That is what is meant by equilibrium constant for a reaction at equilibrium. So that is it. We'll now look at the types of equilibrium constant. So on the whiteboard, we're looking at the types of equilibrium constant. There are two major types. We have Kc and Kp. K subscript C is called equilibrium constant with respect to concentration. So that C there means concentration. While K subscript P is called equilibrium constant with respect to partial pressure. So let's begin by learning how to write Kc. So to write Kc, they have been explained before. The example we took previously, when you have AA plus BB, giving us at equilibrium CC plus DD. So Kc written as the concentration of the product, that is C raised to power C, multiplying themselves, D raised to power D, all over that of the reactants, A raised to power A, and then B raised to power small b. So that is the Kc expression. That is very simple. So the product's concentration raised to each of the raised to the power of the stoichiometric number of moles over that of the reactants raised to their number of moles. But mind you that when you're writing Kc, only aqueous and gases or gaseous state are represented. So we only represent substances that are in aqueous state and in gaseous state. You don't represent substances, they don't represent solids. Solids and pure liquids, like water in liquid state, are not represented. So that means when you want to write the equilibrium constant expression, so we assume that these substances are all in gaseous or aqueous, or a mixture of gaseous and aqueous state. So if C were to be solid or were to be liquid, it will not appear here. You remove it. Or if A or B were to be liquid or solid, you remove them. So you only represent only aqueous and gaseous state in writing of your Kc. You don't represent solids or pure liquids. How do you know aqueous? When you see AQ, that means aqueous. Gas, when you see G, that means gas. Solid, when you see S. Liquid, when you see L as a subscript. So solids and liquids are not represented in equilibrium constant expression. Note that very well. Then we'll now look at how to write our Kp. So we have seen how to write our Kc expression, then how to write Kp expression. To write Kp, that Kp is mainly for a gaseous system. For instance, let's say A is in gaseous state, B is in gaseous state, and then C is in gaseous state. So for you to write, because why do we use for gases? Because gases are affected by pressure. Liquids and solid are not affected by pressure changes. So the Kp is for gaseous system, where all the reactants and products are all in gaseous state. To write Kp now, how do we go? Similarly, we use the pressure of the product. We'll now write Pc. That C is the product. That means partial pressure of the product C raised to the number of moles C. So this small c, let me just, not confuse it. Let me call here S, call here Y. We call this place small m, call this place small n, to avoid confusion. So this means this is the product, partial pressure of the product raised to the power S, which is the number of moles, multiplied by the partial pressure of the other product, which is D, raised to the power Y, all over the partial pressure of the reactant, Pa, raised to the number of moles, M, multiplied by the partial pressure of the other product, B, raised to the power N. So you see that it's similar to Kc expression, except in Kc, you apply a square bracket for concentration. When you're writing Kp, you use P to represent the partial pressure of each of the substances, as you can see it on the whiteboard. So let's take a simple exercise. So look at the question on the board that says, write the equilibrium constant expression for each of the following reactions. For each of the reactions as indicated. You can see the reactions on the board. So we're going to write the equilibrium constant expression for each of the reactions as indicated. Going to number 1, we have hydrogen molecule, gaseous, plus sulfur, solid. You know, hydrogen sulfide, gaseous. We're going to write the Kc expression. So let's start with the first one. To write the Kc for the first one, concentration. The product is hydrogen sulfide, H2S in square bracket, all over. The reactants will have hydrogen in square bracket, gaseous state, H2. Then the next reactant is solid. Solids are not expressed in the equilibrium constant for concentration. So we don't represent solid, we don't represent liquid, we don't represent gases. So we have gas, solid, and gas. So our interest is on the gaseous state. We don't represent the solid. So it's wrong for you to write the solid because solids and liquids have large volume and large density in solution. So we don't represent them in the equilibrium constant expression. So the answer for number 1 is as indicated above. Go to number 2 question. Looking at number 2, we are asked to write Kc for number 2. We look at the substances, the states first. This one is in solid state S, so it's not represented. This is gaseous, solid, not represented. So what should be on top? Since we don't have any solid on top, we're going to write numerator. We're going to now write 1 all over, replacing this solid as a constant 1. Then this one, SO2, then all multiplied by oxygen. The oxygen has a half mole in front, now right, raised power half. So this is the Kc expression for number 2 question. You can see that. So going to number 3. To write the Kc for number 3 expression, let's look at the states. This is gaseous state, this is solid. Solid is removed. Gaseous, solid is removed. So the Kc expression now we are left with hydrogen in square bracket. The number of moles is 4, raised power 4, all over Going to the reactant, we're left with steam, H2O. Some people say that water is not represented, but this water is in gaseous state, not in liquid state. So that why it's represented. So you have it. So the correct expression for number 3. Now going to number IV 4. The fourth example, let's look at the states of the substances. Gaseous, aqueous, liquid. Water is in liquid state. We'll remove this water. Solid, removed. So we'll represent the products. So our Kc becomes concentration of sodium hydroxide. The number of moles in front is 2 multiplied by the concentration of hydrogen gas. Nothing under. What should be under now be 1 because these ones are not expressed, being solid and liquid state. So you can look at the water in the question previous I and the water here. The the water was represented because the water is in gaseous state, but in this one is in liquid state. That one is ignored. We'll go to number 5. So we have Kc expression for this reaction. So that let's bring it up. So to get the Kc expression for this reaction, our Kc becomes the concentration of ammonia, the product ammonia, to what power? To power 2 all over that of nitrogen, then multiplied by that of hydrogen, to the power 3. Number of moles taken into consideration. Number of moles here is 1, so nothing is up. Here is 2, and here is 3. They will also write Kp. The Kp expression for the same equation, since it's a gaseous system, is now the pressure of ammonia, NH3. Partial pressure of ammonia raised power 2 on the P, all over the partial pressure of nitrogen multiplied by the partial pressure of hydrogen, the number of moles raised power 3. So you can see the 2 and the difference between the 2. So having done that, the question we'll ask ourselves is that the Kp and Kc expression, are they the same thing? No, they are not the same. Is there a relationship between Kc and Kp? Yes, they're related. We should know that the Kp begin by RT multiplied by, so that's the relationship between Kc and Kp. Okay, there's an error. Let's correct it. Okay, we have to bring in Kc. That is Kp equal to Kc into RT. Then that is it. Relationship between the two of them. Where Kp, the equal constant with respect to partial pressure of the gaseous system. Kc is the equal constant with respect to concentration of the gaseous system. R is the gas constant. So R had the value of 0.08, I think 821 atmosphere per liter per mole per Kelvin. The same R can still be given as 8.314 joule per mole per Kelvin. So R can be given as this, or in standard unit, that the SI unit, R had this value. The value of R differ depending on the quantities you're working with in the calculation. So that is your R. T is the temperature in Kelvin. And then delta N is the change in mole of the gaseous system. Delta N is given by summation of the number of moles of gaseous product minus summation of the number of moles of gaseous reactant, number of moles of gaseous product, number of moles of gaseous reactant. For instance, let's say we have this reaction, nitrogen plus hydrogen, giving us ammonia. So number of moles of the gaseous reactant is going to be, there's 1 mole of nitrogen here, plus 3 moles of hydrogen, that gives us 4 moles. Number of moles of gaseous product, there's only 1 gaseous product, which is 2 moles. So the change in mole becomes product minus, that is 2 minus 4, giving us minus 2 for this particular reaction. So you see that. So having done that, we'll go over to another thing. So we have the law of mass action on the board. The law developed by 2 gentlemen called Goldberg and Wedge. The law of mass action says that the rate of reaction of substances in a chemical reaction is directly proportional to their active masses. Active masses here represents concentration. The rate of reaction of substances in a chemical reaction is directly proportional to their active masses or concentrations. So let's explain this with an example. For instance, let's say I have an equation like a hypothetical example, A plus B giving us C plus D. Now, if you want to write from this law, rate is proportional to concentration. Now, if you want to write the rate for the forward reaction, because this is the forward reaction, the first arrow, the reactant going to the product, and I write RF is proportional to the concentration of A raised to the power of its number of moles to that of B raised to the power of its number of moles. You see that? Where RF means rate of forward reaction. Then I can also write RF equal to KF, then A, then B to the power B. What does KF mean? KF is nothing but the rate constant of the forward reaction. Now, since the reaction is reversible, we can still write the same expression for the backward reaction. We now write R, rate of reverse reaction, is proportional to the concentration of the products raised to their number of moles. You can see that. So we can now bring in the constant. We now call it Kr into C to the power C, D raised power D. We can call this equation 2. So this is the rate of reaction for the forward reaction, and this is the rate expression or equation for the reverse reaction. So you write the forward using the reactant, write the reverse using the backward. So Kf is the rate constant for the forward reaction, Kr is the rate constant for the reverse reaction. So having done that, now we'll now divide equation 1 by 2. Divide equation 1 by 2. That means divide RF by RR. So let's write it up. Equation 1 is Kf A to the power A, B to the power B, equation 1. Equation 2 is RR, Kr equal to C to the power C, and then D to the power D, equation 2. So we have to divide equation 1 by 2. What it means is I'm going to divide this by that. RF over RR equal to, or before, no, not division. Sorry for the error. So at equilibrium, see the rate of forward reaction, this the rate of backward reaction. So at equilibrium, remember at equilibrium, the rate of forward is equal to the rate of backward reaction. Good. So I can equate 1 to 2, not divide, equate equation 1 to 2. So at equilibrium, the two of them are equal. You can now say Kf A to the power A, B to the power B for the forward reaction will now be equal to Kr C to the power C and D to the power D. Because at equilibrium, the two rates are equal. If this is equal to this, to that, I mean this is equal to that, as you have it here. So having done that, let's divide both sides by Kr. If we divide both sides by Kr, I now have Kf over Kr into A, then B equal to C to the power C, then D to the power small d. Then divide both sides again by this concentration by A to the power A, B to the power B. So divide both sides by this. You now have this and then that. When you have done that, this will cancel out. So you are left with Kf over Kr. Kf over Kr equal to C to the power C, then D to the power D, all over A concentration to the power small a multiplied by B to the power B. I know that at equilibrium, as we said, at equilibrium, we can now replace this ratio, the ratio of the rate constant of the forward to the backward becomes the equilibrium constant, which is our Kc. When I become this, so that proves that to write Kc is nothing but the concentration of the products to the number of moles over that of the reactant to the number of moles, as we have proven it in using the law of mass action. So you see, it's very simple to understand. Now we'll look at the significance or the value of the equilibrium constant. So what does it mean when the value of K is large or when the value of K is small? So number one says when the value of K is large, that's when K is more than one whole number. It means that the forward reaction is favored and the reaction is nearing completion. So when the value of K is more than 1 or is large, it means that much of the product have been formed and the reaction is nearing completion. Number 2, when the value of K is small, that when K is less than 1, it means that only little amount of the reactant have been converted to the product. That means the reaction is still incipient. The reaction has not gone far. That means only little amount of the reactant have been changed to product. So that is very important to note. Now look at another technical term used in chemical equilibrium called reaction quotient, represented with the symbol Q. Sometimes most of us confuse the reaction quotient with the equilibrium constant. They are two different things. So look at the definition of reaction quotient. We say this is the ratio of the concentrations of the products raised to their stoichiometric moles to that of the reactants at any given instant or any given time. Look at that example. A, small a, capital A plus small b, capital B, giving you small c, capital C, then small d, capital D, where the capital letters are the reactants and products, and the small letters are the number of moles. So you have the expression for Q, which is consist of C raised to the number of moles of C, multiplied by that of D raised to the number of moles of D, all over that of the product, that of the reactant A raised to small a, and then B raised to power small b. This looks more like the equilibrium constant expression K, but what the difference? Look at equilibrium constant is written, the definition, if I change it and replace this at equilibrium, then this becomes K. But at any given time, this becomes Q. So if I write this expression when the reaction has not reached equilibrium, that could be Q. When the reaction has not reached equilibrium, that becomes RQ. If the reaction reaches equilibrium, that means Q now becomes equal to K if the reaction is at equilibrium. But when the reaction has not reached equilibrium, we cannot call this our equilibrium constant. So that's why we have to say at any given time. So we'll write the ratio of the concentration of the product raised to the number of moles over that of the reactants. Then what we are writing is the reaction quotient if the reaction has not reached equilibrium. But once it has reached equilibrium, then this RQ turns to K. Just like we have our Kp and Kc, we still have Qc and Qp. Reaction quotient with respect to concentration and reaction quotient with respect to partial pressure. So having done this, the next aspect we're going to enter now is calculations. Calculations is only meant for those in first year university, A-level, JUPEB program, or any A-level program. So that was the calculation. While the concepts or the theory is meant for all, whether it's A-level, first year, or those in SS3 secondary school. That is still for you. High school, that is still for you. So let's go to calculations now. Before we go to calculations, we have to look at an important point. So the significance of the value of Q. So Q is the reaction quotient. If the reaction quotient is less than the equilibrium constant, what does it mean? It means that the reaction proceeds from left to right. What do I mean by moving from left to right? You have a reaction at equilibrium, like this example on the board. To move from left to right means this is the left-hand side of the equation, the product side. This is the right-hand side. So when I would say reaction is moving from left to right, it means the reaction is moving from what? From left to right means it moves from reactant side to the okay, this is already the left hand side, and this is the right hand side. So when I say reaction process from left to right, it means that the for reaction is favored. This is moving from left to right. So we're getting more product than reactants. So that means when Q is less than K, we are getting more product than reactants. Then if Q is greater than the equilibrium constant, reaction proceeds from right to left. That means the arrow will not change. The from left to left means from right going to left. That means the backward reaction is favored, getting more reactants than products. But if Q is equal to K, reaction is at equilibrium. That means the two rays become equal to each other when Q is equal to K. So we can go ahead with our calculations meant for A-level students. Calculations all true for now. So I have a question on the whiteboard. The reaction between nitrogen and oxygen to give us 2 molecules of nitrogen 2 oxide NO. It says at 200 Kelvin, the equilibrium constant Kc for the above reaction is 0.40. If the concentration of nitrogen and oxygen gas are both 0.50 mole per dn cube, while that of NO is 0.30 mole per dn cube. Question is the system at equilibrium? So we don't know. We're going to find out. All you have to do is you calculate the reaction quotient for this reaction. So let that the expression for reaction quotient QC for the above reaction, which is the concentration of NO, the product, raised to power 2 over that of the reactants, that is nitrogen multiplied by oxygen. For the equation, the concentration of nitrogen 2 oxide NO is 0.30. The concentration of nitrogen as well as oxygen are equal, given to us. Both of them is 0 for both of them 0.5. So with these values, we're going to calculate our QC, making substitution. I have concentration of NO, which is 0.30 all squared, all over that of nitrogen 0.50 multiplied by that of oxygen 0.50. That gives us square d, that gives you 0.06 multiply d, that gives you 0.25. So when you divide 0.06 by 0. That is okay, that is an error. If you square this, it's going to get 0.09, not 0.06. So divide 0.09 by 0.25. So they bring the equation, the calculations up for all to see very well. The substitution QC, that is 0.30 for the numerator, over the denominator 0.50 for nitrogen, oxygen 0.50. So if you square this, you have 0.09, 0.25. Divide 0.09 by 0.25, you have our QC as 0.36. So that is the equilibrium constant. The reaction quotient for the reaction. But in the question, we are told that the equilibrium constant Kc, from the question given to us, that the value of Kc is 0.4. Kc is 0.4. Well, now, look at the value of Qc. Qc is 0.36, is less than the value of Kc, which is 0.4. And we are told that initially, when we look at the importance of the value of Qc, you see that when the Qc value is less than Kc, it means that the reaction, the forward reaction is favored. So indeed, we can say that the reaction proceeds from left to right. So we are getting more of this now. Reaction is moving from left to right. So the equilibrium will shift to the right. So moving the forward reaction further. Because whenever the value of the reaction quotient is less than the equilibrium constant, the reaction moves forward, favoring the forward reaction from our calculation. So go to the next example and next calculation, please. So the next we're going to look at is calculations on Kc and Kp. We have an equation there where we have phosphorus pentachloride being decomposed to phosphorus trichloride and chlorine gas. Question is, the Gould's constant Kp for the above reaction at 300 degrees Celsius is 11.5 atmosphere. What the value of Kc for the reaction at 300 degrees Celsius? In bracket, 1 atmosphere is 101,325 Newton per meter squared. The gas constant in standard unit, JUPEB mole per Kelvin, is 8.314. So look at this, we're looking for Kc when we're given Kp. My equation I gave to you, the connection Kp given by Kc into RT raised power delta n. So that's the equation you need. Since they gave you Kp, you're looking for Kc, so that's the connectivity you need. Having done that, then this is what we have. Our temperature is 300 degrees Celsius. Convert to Kelvin by adding 273. That give you 573 Kelvin. Convert your temperature to Kelvin. Then let's find the number, change the number of moles. Change the number of moles will now becomes the summation of number of moles of gaseous product minus summation of moles of gaseous reactant. The product, number of moles, 1 plus 1, that is 2 moles this side. Reactant is only 1 mole, so 2 minus 1 give us 1. So the change in moles is 1. 1 mole there and 1 mole there giving you 2. And then 1 giving you 2 minus 1, this is 1 mole, or difference of 1. So having done that, now let's look at the value of R given to us. Okay, let's look at the value of Kp. Kp given to us. So we can write the upper side and use the upper side of the board. So our Kp is given to us as 11.5 atmospheres. So that the equilibrium constant with respect to partial pressure, 11.5 atmosphere. The value of our R is not, we have 8.314 joule per mole per Kelvin. Remember I told you that there are two values of R. I gave you the first one as 0.082 atmosphere per liter per mole per Kelvin. This is the scum value of R. But before you use this one, you have to see whether the values, the units of you have in this R must reflect in all these quantities you're going to use. Mole, this is 1 mole reflected here. The change in mole. Kelvin, that is temperature reflected here. Then joule, this is atmosphere. So these two units are not uniform. This is the standard unit. What is the non-standard unit? So you cannot use this R to do your calculation. It will be an error because this is not carrying atmosphere. The two units are not uniform. They're not concord. So what you're going to do? You're going to do is you're going to convert this atmosphere to the SI unit of pressure to Newton per meter squared. So we now have conversion. 1 atmosphere giving us 101,325 Newton per meter second. Then therefore 11.5 atmosphere, when I give 11.5 times 101,325 Newton per meter second. So you convert it to the standard unit. So you multiply the two and get what you need. And that gives us 11,652 37.5 Newton per meter square. So that it be in the same standard unit as the joule. So when you have done that, you can then embark on your calculation. You have Kp equal to Kc RT root delta n. You're looking for Kc. You make Kc the sort of formula. Kc becomes Kp all over RT raised power delta n, making Kc the solid formula. So you can go ahead and make your substitution. To make your substitution now, the value of your Kp is the converted value, 11,652 37.5. That becomes your Kp all over. The value of your R, 8.314. Temperature, which is 5 centigrade in Kelvin. raised power. Change in mole is 1, so which means no difference. So when you solve this, you have your final answer as 245 at the final answer. So the value of our Kc for that reaction. So we'll take another example and then see what we can make out of this. So look at an example on calculation of Kc and Kp. The first example, we're able to calculate our Kc. On this other one, we're looking for our Kp. So the equilibrium constant Kc for the reaction at 25 degrees Celsius is 2.45 times power minus 4 mole per liter. Calculate the value of Kp, and you have the reversal gas constant, the big R, in the other unit, which is 0.0821 atmosphere per liter per mole per Kelvin. So let's convert our temperature first. T becomes 25 plus 223, giving us 298 Kelvin. The value of our Kc is 2.45 minus 4 mole per liter, as given to us in the equation. Then let's look for the change in moles, which is the number of moles for the product, which is 2 moles. The minus that the reactant. Reactant will have 1 mole in front of nitrogen and 3 moles in front of hydrogen. That is 2 minus 4, giving us minus 2, negative value now, mole. So having done that, we look at we're going to apply the formula Kp equal to Kc into RT delta N. Before we make our substitution, we have to look at the unit of R, where the units are all reflected in what's given to us. So you see that Kelvin is there, mole is there, liter is also there. So that is concord, that is okay, nothing missing, because our answer will not be in atmosphere. We can go ahead and substitute. So our Kp now becomes equal to the value of our Kc. Let me write the upper part, write the equation and make use of the upper part to solve. So our Kc making our substitution, we have let's go through it once more, please. So since we have our temperature at 25 degrees Celsius, convert it to Kelvin by adding 73, you have 298 Kelvin. The value of our Kc is 2.45 power minus 4. Then our number of moles, change in moles, is 2 minus 4 minus 2 from the balance equation provided. Then we need this equation Kp, Kc, RT raised power delta N. Then you substitute Kp, our Kc is this value, 2.45 power minus 4, bracket opens. Our RT, R is 0.0821, the gas constant given to you, times. Temperature is 298, raised power, the change in mole is minus 2 there. Then, if you look at that, you can now evaluate, that is, you can bring this one under, from the law of indices, when it comes under, this minus 2 turns to plus 2. So that is it. So you remove the minus sign, you have this, then divide this by that, you have 4.09 to the power minus 7 atmosphere at the value of our Kp. So when you're evaluating such problems, you have to be very careful, note the value of R, that is the R constant. So, and know which one to use when it's appropriate. The value of R must correspond, the unit on R, like if R is given to you as 8.314 joule per mole per Kelvin. For you to apply this to solve directly, your temperature must only be in Kelvin, of course. The change in mole, delta N, must be reflected, that is mole. Then your pressure must be in Newton per meter squared. That is your Kp, must be in this unit. If it's an atmosphere, they must convert, as I did in the first example. So if the Kp is expressed in atmosphere, you must convert by using 101325, as I did in the first example. But if it's not in atmosphere, is in this, you can apply this constant directly in the formula and then calculate. So you see how to do that or how to go about it. So we'll take another example. We'll take another example on this, and then we'll move on. So at this session, we're going to look at how to calculate the value of the equilibrium constant K from experimental data. Have an equation above between nitrogen molecule, 1 mole of nitrogen plus 1 mole of oxygen, giving us 2 moles of nitrogen monoxide or nitrogen 2 oxide. Question reads, at 2290 Kelvin, the equilibrium constant for the above reaction is 9 times power minus 4. Calculate the equilibrium concentration of nitrogen if the equilibrium concentration of nitrogen 2 oxide and oxygen are 3.6 power minus 4 mole per dn cube and 0.0089 mole per dn cube respectively. So in this reaction, we're given the equilibrium constant. So our Kc is given to us as 9 times power minus 4 for the reaction. I mean, the reaction is presumed to be at equilibrium. And we're given the equilibrium concentration. So the concentration of NO at equilibrium, EQ means equilibrium, is 3.6 power minus 4 mole per dn cube. And that of oxygen at equilibrium is 0.0089 mole per dn cube. So we are given all this information and we are asked to calculate the equilibrium constant. So we're asked to calculate, the equilibrium concentration of nitrogen. So the first thing we have to do is we're going to write the expression for the equilibrium constant. Since the reaction is at equilibrium, we have Kc, the equilibrium constant for nitrogen, the constant of nitrogen 2 oxide raised to power 2 all over that of nitrogen multiplied by that of oxygen. So having done that, we'll now make a substitution. The value of our Kc is 9 times power minus 4. The value of the equilibrium concentration of nitrogen 2 oxide is 3.6 power minus 4 all squared all over the concentration of nitrogen given to you is what we're looking for. We're asked to look for that, so we'll make it unknown. And then the concentration of oxygen given to us as 0.0089. So the equilibrium concentration of oxygen and the equilibrium concentration of nitrogen 2 oxide. So we'll now work by cross multiplying. We'll now have 9 times power minus 4 multiplied by nitrogen multiplied by 0.0089 equal to 3.6 power minus 4 squared. So we'll now work. Then multiplying 9 power minus 4 by 0.0089 will give us 8.01 10 power minus 6. Then multiply by the concentration of nitrogen at equilibrium equal to square this side 3.6 power minus 4 all squared give us 1.296 power minus 7. So having done that, you now make the concentration of nitrogen the solid formula. So the concentration of nitrogen at equilibrium, the equilibrium concentration now become 1.296 power minus 7 all over 8.01 power minus 6. So solving this, we get our final answer as 0.0162. So this is the concentration of nitrogen at equilibrium solved on the board. So remember that the equation assumes that the reaction is already at equilibrium. So we'll take a second question still on how to calculate concentration from equilibrium constant. We have a reaction about between 1 mole of hydrogen gas and 1 mole of iodine vapor or gas to produce 2 moles of hydrogen iodide. Question says The equilibrium constant of the above reaction at 448 degrees Celsius, that the Kc is 50.2. Calculate the mass of hydrogen iodide that is in equilibrium with 1.25 mole of hydrogen and 63.5 grams of iodine at this temperature. So you can see that. So let us list what we have from the equation. The value of our Kc is 50.2. So the number of moles of hydrogen at equilibrium is 1.25 moles. So this number of moles can represent concentration, since they do not give us volume in this equation. So, but number of moles is directly proportional to concentration. So we'll have to use that concentration. Then they give us the mass of iodine at equilibrium. So mass and mole cannot move along. So we're going to convert this mass to moles of iodine. So you know that the number of moles is given by mass over molecular mass. So the mass of iodine is 63.5. The molecular mass of iodine is what they give us in bracket is the atomic mass of iodine. And you know that iodine is a molecule, whether it's I2. So we're going to multiply this by 2 to find the molar mass. So you now have 63.5 all over 254. And that will give us 0.25 moles of iodine. So the concentration of iodine now is taken as at equilibrium as 0.25 mole. You see that? So we're looking for the mass of hydrogen iodide that be in equilibrium with this. So it's assumed that the reaction is at equilibrium. So having done that, how do we go about it? We'll continue on the upper side. We'll first of all write the equilibrium constant expression Kc, which is the concentration of hydrogen iodide, the product to the power 2, all over that of hydrogen multiplied by that of iodine. So you have that expression. The value of your Kc substitution becomes 50.2. The concentration of this one, you don't know it, you can call it S. Then S square because of the power 2. The concentration of hydrogen is 1.25 multiplied by that of iodine, 0.25. So you can cross multiply. So they can make S square the formula. So when you go multiply, S square becomes equal to 50.2 times 1.25 times 0.25. So apply the values, you're going to get 15.7. 15.7. So you make N the subject. So if S squared is 15.7, that means S becomes square root of 15.7. When you find the square root of 15.7, you'll be getting 3.96 mole. 3.96 mole. So the concentration or the amount of hydrogen iodide is 3.96 mole. But we're looking for the mass. They say what mass of hydrogen iodide will be in equilibrium. Look for the mass of hydrogen iodide. So find the molar mass of this compound. The molecular mass of hydrogen iodide is given to us as 1, be the atomic mass of hydrogen, plus 127, atomic mass of iodine, giving us 128. And you know that mass is mole times molar mass. That becomes 3.96 times 128. When you multiply, you have your final answer, which is 506.9 grams as the final answer. 506.9 grams. We're going to take more examples still on calculation of concentration from equilibrium constant. So let's look at this problem on the board. The reaction between carbon 4 oxide CO2 plus hydrogen, giving us carbon 2 oxide CO2 and hydrogen on the other side. And that should not be hydrogen. And steam, this is H2O. Let's correct it on the other side. So the question says the equilibrium constant Kc for the above reaction is 1.6 at 690 degrees Celsius. What is the concentration of each substance at equilibrium in a mixture prepared by originally placing 0.5 mole of CO2 and 0.5 mole of hydrogen gas in a 5.0 liter flask at 690 degrees Celsius? So if you look at this question, they give us the value of Kc. The equilibrium constant is 1.6. They give us the number of moles of each reactant. So number of moles of CO2, N is number of moles, is 0.5 mole, initial mole, and then the initial number of moles of hydrogen in the flask is also the same 0.5 mole. The volume of the flask given to us is 5.0 liters. So with this, we can calculate concentration since they give us the volume. Now, concentration, let me write the upper side. Concentration can be calculated with the formula concentration given by N in mole all over V in liters. That is concentration. So I'm going to find the initial concentration of CO2. The bracket means concentration of CO2. I means initial, using N over V. The number of moles of CO2 is 0.5. The volume of the container is 5 liters, given to you down there. That gives us 0.1 mole per liter. The same thing applies for the initial mole of hydrogen in the flask. We're going to have N over V, initial concentration of hydrogen, in the flask. We have the same number of moles of hydrogen is 0.5, the same volume of flask, 5 liters. That gives us the same 0.1 mole per liter. So having obtained the initial mole, remember that this concentration, not the concentration at the equilibrium, that's the initial concentration introduced into the flask, not the equilibrium concentration. So you have to know the question, understand the question very well. Then, what then do we do? We're going to prepare what I call the ICE table. The ICE table. What means of ICE? ICE table means initial change equilibrium table. Initial change equilibrium table. So the table will look like these: substances. Then I write here the reactant CO2 and the other reactant hydrogen. The product will have CO. The other product will have steam, water vapor. So these are the concentrations. So the first I means the initial concentrations. Initial concentrations, initial conc, that is initial concentrations in this abbreviation of them. So have INI, initial, TIAL, initial concentrations of them in the flask. The initial concentration of CO2 have been calculated as 0.1. I'll have it above 0.10. The initial of this is hydrogen is 0.10. The initial concentration of these products will be 0 because what means initial concentration? It means the initial amount before the reaction began. So before the reaction began, there were no product formed. So the initial amount of these two introduced, the concentrations are this and that, 0.1, 0.1. So there was no product formed initially. That is why the product have 0 concentration initially. Then we now look at the change in concentration. The change in concentration. That is C, meaning change. What do I mean by change? Let's go to the equation of the reaction. The equation of reaction says CO2 plus hydrogen giving us CO and water vapor. The ratio is 1:1:1:1, the supreme number of moles. So let's assume that S moles of CO2 decompose to give the product. Then we will still have S moles of hydrogen that decompose because the ratio is 1:1. So S moles goes out from this one, S moles will still go out from this one. To produce also S moles of this and S moles of that because they have equal stoichiometric ratio. So let's say the change here be S. The change on this one will be also the same S. This one also be S, S. So since this S moles or S amount is leaving from CO2 and leaving from hydrogen, we're going to put minus being so that to show that the reactant is decomposing. This is the amount that is leaving from the reactant concentration to form product, and also minus on this side because this is a reactant. For the product, we say plus because the product, this amount is added on the product side. So we now look at the equilibrium concentration. That is this ICE table. To find the equilibrium concentration for the reactant. So this is the initial amount. This is the amount that had added from this initial amount. So at equilibrium, the concentration of the reactant will now become 0.1 minus S, removing this from the initial amount. The same thing here, 0.1 minus S. For the product, it's going to be 0 plus S, giving us the same S. That is 0 plus S, giving us the same S. For this other one, the same thing, 0 plus, because the product is increasing amount, while the reactants are decreasing amount, giving us the same S there. So having done that, we have prepared our ICE table. We can now go ahead and write the equilibrium constant, Kc expression for this reaction. We have Kc will now become equal to constant of CO multiplied by that of steam, not water. It's water, it won't appear. All over CO2 multiplied by hydrogen. So make a substitution after writing the equilibrium constant expression from the ICE table. The concentration of CO2 from that table is taken as S. That of steam taken as also S. That of CO is 0.1 minus S. That of hydrogen is taken as 0.1 minus S. So having done that, we now remember that our Kc is 1.6 from the equation. So having done that, we now have 1.6 equal to S squared all over 0.1 minus S all squared. So having done that, since both the numerator and the denominator are all squared, we can include the numerator and the denominator inside the same square bracket. You can say S all over 0.1 minus S, the two of them are squared. So how do we unsquare the right hand side? We take the square root of both sides. So take the square root of both sides, we now have 1.6 square root equal to S all over 0.1 minus S. So we now find the square root of 1.6. The 1.6 give us 1.265. We solve up. We now have 1.265 equal to S all over 0.1 minus S. Having done that, we can now cross multiply. When we do that, we now have 1.265 into 0.1 minus S equal to S. So you open the bracket, you now have 0.1265, that is multiplied by that, minus 1.265S equal to S. You collect like terms. Collecting like terms, we have 0.1265 equal to S plus 1.265S. So 0.1265 give us 2.265S. So you make the solve the formula by dividing both sides by 2.265. So S becomes 0.1265 all over 2.265. S becomes 0.0558. So 0.0558 mole per dm cube. So you're asked to find the equilibrium concentration of each of the substances. So the equilibrium concentration from the equation of CO2, we say is going to be 0.1 minus S. So bringing S here, now they get the concentration of CO2 going to be 0.1 minus 0.0558. So that gives us 0.0442. So that the equilibrium concentration of CO2, they are one of the reactants. And also from the ICE table, the equilibrium concentration of hydrogen is 0.1 minus L, same as that of CO2, which if you substitute the same thing here, you still get 0.0442 mole per dm cube. They go into the product. The equilibrium concentration of carbon 2 oxide from the IC table is given to you as S, the value of S, which is 0.0558. That is this. Also, the equilibrium concentration of a hydrogen of steam, from the product from the IC table is the same S, which is 0.0558 mole per dm cube. So that is a very simple illustration. We'll take another example. So look at the next question on the board. See on calculation of concentration from a equilibrium constant. We have the reaction between hydrogen and iodine vapor giving us 2 moles of hydrogen iodide. The question says the equilibrium constant Kc for the above reaction is 55.17 at 699 Kelvin. If 1.0 mole each of hydrogen and iodine vapor are contained in a 0.5 liter flask at 699 Kelvin, calculate the equilibrium concentration of the substances, that the reactants and the products. So this question is more like the previous one that we did. So they gave us the number of moles, the initial number of moles of the reactants, hydrogen and iodine. So we can say the initial mole of hydrogen, the initial mole is 1.0 mole. The initial mole of iodine in the equation is also 1.0 mole. The volume of the container is 0.5 liters. Since we have mole and volume, the first approach, or the first thing we have to do, is to find the concentration of each of the reactants. Using the formula for concentration as we used in the previous example, the concentration of hydrogen, again by mole over volume. Number of moles is 1.0 mole. Volume is 0.5 liters. That gives us 2 mole per liter of hydrogen. In the same manner, I can still calculate the concentration of the initial concentration of iodine using the same mole over volume. The mole is the same 1.0 of iodine initially over the volume 0.5, giving us the same 2 mole per liter of iodine initially. So having obtained the initial mole of a concentration of iodine, the reactants, and the initial concentration of hydrogen as 2 mole per liter each. And bearing in mind that the equilibrium constant is 55.17. We're now going to prepare our ICE table, ICE which I call initial change and equilibrium table, as we did in the previous example. So let's wipe this out. So our Kc, remember, remains 55.1. So we're going to make use of it later on. So we're going to prepare a table: substances or species, the reactants, hydrogen, concentration, iodine, and then hydrogen iodide concentration. We're now leave the initial concentration of each of the substances. Initial concentration of each of the substances. From what we have on the table, the initial concentration of iodine and hydrogen are calculated as 2.0, 2.0 being the reactant, the initial amount introduced. And when they were introduced, that was before the reaction. There was no iodide formed, so here it becomes 0. The product was not formed initially. So having done that, so the next thing we'll go to now is the change in concentration. So change in concentration. Before we do that, we'll go to the reaction, the reaction stoichiometry. have one, the ratio, mole ratio 1 here is to 1 there, and then 2 over there. So 1 mole of hydrogen combined with 1 mole of iodine to give us 2 moles of hydrogen iodide. So assuming that S moles of hydrogen reacted, S moles of iodine will also react because the ratio is 1:1, and 2 S moles of iodine will be produced. That is 2 times S. So change in concentration is minus S for hydrogen, minus S for iodine, the reactant, and then plus 2S for hydrogen iodide being produced. So, having done that, we'll now move to the equilibrium concentration. The equilibrium concentration. So, that is it. For the reactant, the difference between the initial and the change. That becomes 2 minus S for this one. For this other one, also the same 2 minus S for iodine. For the product, the change is the addition of the 2, which is 2S plus 0. I mean, that the group concentration, that becomes 2S. Please not change for the product. So, having done that, we can now write our equilibrium constant expression given as Kc equal to the concentration of the product, that is hydrogen iodide, raised power 2, over the concentration of the reactant, hydrogen, multiplied by that of iodine, that's the equilibrium constant expression. Having obtained that, we can make our substitution. The equilibrium constant of hydrogen constant of the reaction is 55.17. So I have 55.17 equal to the equilibrium concentration of hydrogen iodide is 2S. We now have 2S all squared all over. That of hydrogen is 2 minus S, the equilibrium concentration of hydrogen. Iodine also 2 minus S. So you see that this example is similar to the previous one we did. So we can write the table and use the upper side for the solution. So we can bring this in up. 55.17 equal to 2S all squared all over 2 minus S all squared because they are the same. Now, since both the numerator and the denominator are both squared, I can include them in one square bracket. I will now have 55.17 equal to 2S all over 2 minus S all squared. So, how do we unsquare the bracket? We take the square root of both sides. We now have square root of 55.17 equal to 2S all over 2 minus S. So find the square root of 55.17, and that will give us 7.43. So we now have 7.43 equal to 2S all over 2 minus S. We then cross multiply. We now have this. So we have 7.43 into 2 minus S equal to 2S. So 7.43 times 2 will give us 14.86. 14.86 minus 7.43 times S give us 7.43S equal to 2S. Connecting like terms, 14.86 give us 2S plus 7.43S. So moving minus 43 to the right hand side, you have that. Then we go up, wipe this side. We now have 14.86 equal to 2S plus this give you 9.43S. S becomes 14.86 all over 9.43. When we divide that, the value of S give us 1.58. 1.58 at the value of S. Molar or mole per dm³. So we're asked to find the concentration of each substance at equilibrium. From our ICE table, the concentration of hydrogen at equilibrium is equal to that of iodine at the table. In that equation, we have 1 mole of iodine and 1 mole of hydrogen reacting together for the balance equation. So, and that is what we have as 2 minus S from the ICE table. So that becomes 2 minus 1.58, since S is 1.58. So when you subtract, we have 0.42. So the concentration of hydrogen and iodine at equilibrium is 0.42 mole per dn cube. Then what of the concentration of hydrogen iodide, the product? The concentration of hydrogen iodide, which is the product from our IC table, hydrogen iodide, we say is going to be 2S at A, which is 2 times 0.42. That is 2S. So sorry, S is not, S is 1.58. So 2 times 1.58, and that will give us 3.16 mole per dm cube. So you see that this question is similar to the previous one that we solved. So we'll take another problem. So now let's look at another problem showing how to calculate concentration from when we're given the equilibrium constant of a reaction. So we still have a reaction there between hydrogen, 1 mole of hydrogen plus 1 mole of iodine gas, giving us 2 moles of hydrogen iodide. Question says the equilibrium constant Kc for the above reaction at 120 degrees Celsius is 2.45. If the initial concentrations of hydrogen and iodine are 0.1 mole per dn cube and 0.5 mole per dn cube respectively, calculate the equilibrium concentration of the substances at 120 degrees Celsius. So look at this problem now. We're going to list what was provided for us. The parameters given to us are the initial concentrations of the two reactants. So the concentration of hydrogen, we write it as this symbol initial into our 0.1 mole per dn cube. That of iodine vapor, initial given to us as 0.5 mole per dn cube. So in this particular problem, we are not going to calculate concentration because they are already given to us direct. We're not going to use mole over volume because they give all the concentration direct. And then we are asked to, we're given the value of Kc. So the Kc value, we can write it here as 2.45 for the reaction. So we're going to build also our ICE table. And ICE means initial, change, and equilibrium table. So build our table now. So we have the substances. We now write the concentration of the reactants first, hydrogen. Write that of iodine. You write that of the product, which is here HI. So having done that, the initial concentration means the amount of the solid present before the reaction commences or commenced. So hydrogen is 0.1, iodine is 0.50. This one is 0 because before the reaction commenced, this one is yet to be formed. So there was no product initially. So having done that, we now write the change in concentration. The concentration change in concentration. Let's go refer to the balance equation. If you go to the balance equation, you have to understand the relationship between their stoichiometric coefficients. So ratio is 1 mole, 2 moles. If S moles of hydrogen reacted, S moles of this will also react. While 2 S moles of this will be produced. So S moles removed from this, S moles removed from that, and 2 S moles produced on this other side. So having done that, we now get the equilibrium concentration. So the equilibrium concentration, or concentration in equilibrium, at equilibrium, please. So we now we subtract. It will be 0.1 minus S for this. This one 0.5 minus S for that. While this one is going to be 2S plus 0, that will give you the same 2S. So having done that, we're now going, the next thing to do is to write the expression for the equilibrium constant. So that becomes Kc, that becomes this, the product concentration on top to the power of 2, all over the reactant concentration in square bracket. So we're going to make substitution in this formula using the equilibrium concentrations and the value of Kc. So wiping the upper side to create more space. So the value of our Kc is 2.45. 2.45 equal to the hydrogen concentration is 2s. That is 2s all squared. You can see that all over, because of the two reactants, they're not the same now, they're different. I think it's 0.1 minus s into 0.5 minus s. So you see that this is a different case. The previous two cases we did, the concentrations of the two were equal. We'll square this side, but we cannot square this because they are different. So what do? We're going to expand the denominator. Now have 2.45. This will give you 4s squared. That is 2s times 2s. All over 0.1 times 0.5 gives you 0.05. 0.1 times s gives you 0.1s. Minus s times 0.5 gives us minus 0.5s. Minus s times minus s gives you plus s squared. So that gives us 2.45 equal to s squared all over 0.05 minus 0.1 minus 0.5 gives you minus 0.6s, then plus s squared. So having done that, we're going to now multiply, that you can cross multiply this and that. So when you multiply, we now have 2.45 into 0.05 minus 0.6s plus s squared equal to s squared. So open the bracket. 2.45 times 0.05. So open the bracket, that gives us 0.123 approximately minus 2.5 times 0.6 give us approximately 1.47s. 2.45 times this give you 2.45s squared equal to s squared on the other side. So we'll pull like terms together. Let's move every term to this side. So s squared, or let's bring s squared to this side. You have 0.123 minus 1.47s plus 2.45s squared. Crossing this one, that becomes minus s squared equal to 0. So having done that, we now have 2.45s squared minus minus s squared. So that gives us 0.123 minus 1.47s, then plus 1 point. If you do the mathematics very well, that gives us 1 point, about 1.45 s, 1.45. So let's be very sure of our answers. That gives us, let's go through it once more. 1.4, this is 2 minus 1 here, give us 1.45 s squared equal to 0. Rearrange and make it look like a correct equation. I can bring this one in front. I have 1.45 s squared minus, this one comes next, 1.47 s, this one comes last, plus 0.123 equal to 0, taking the form of a quadratic equation. So we can bring this expression up. We have 1.45 s squared minus 1.47 s plus 0.123 equal to 0. So this looks more like it's not a quadratic equation or expression of the nature as squared plus bs plus c equal to 0. So we'll pick the coefficients now. The coefficient of s squared is a. So for here, a is now 1.45, referring to this. The coefficient of s is b. For this, b is equal to minus 1.47. Take into consideration the sign that is there. And c is equal to 0.123 there. So the formula, we use the formula S used for solving quadratic equation, which is minus b plus or minus b squared minus 4ac all over everything all over 2a. So we'll substitute and solve. So when we solve or substitute, our L becomes equal to minus part of the formula, and our B is carrying that minus. That means minus 1.47 plus or minus, bracket opens, B is minus 1.47, that is minus 1.47 all squared minus 4ac. Our A is 1.45, our C is this, minus 4 into 1.45 multiplied by 0.123. Okay, you see that's what we have there. So let me bring it down to make it clearer. You make substitution, S becomes equal to minus B. Our B is minus 1.4. Remember the formula, there is B already in the minus already in the formula, and B is carrying minus on its own. Then plus or minus B squared, that is minus 1.47 our B all squared. Then minus here 4a, our A is 1.45 times C is 0.123 over 2a. 2a, our A is also 1.45. So you see that. So having done that, we can now solve. Let's go up and wipe this side. So S becomes equal to minus times minus to give you plus 1.47 plus or minus. You now have the bracket open. 1.47 squared. Do it. 1.47 squared give us 2.161. 2.161 minus 4 times this times that. That is 4 times 1.45 times again 0.123 will give us 0.7134. So 0.7134 over 2a, everything over 2a. That is 2 times this, giving us 2.9. So very clear what is inside the square root. 2.161 minus 2.161 minus 0.714 give us about 1.45 approximately. So S becomes equal to 1.47 plus or minus square root of 1.45 over 2.9. So S becomes equal to 1.47 plus or minus, find the square root of this number. Square root of 1.45 will give us 1.204. So 1.204 all over 2.9. So our S will have two values. You're like a quadratic equation, we always have two answers, but we're going to pick the one that gives us a positive answer. because concentration will always be positive number. But we have two numbers here. Let's see now whether they're going to give us positive answer. So 1.47 plus 1.204 all over 2.9, or 1.47 minus 1.204 all over 2.9. So let's see what we're going to get. So plus or minus. The answers are all positive. So we're going to select one of the answers. Decide what we want to select after this. We have 1.47 plus 1.204 divided by 2.9. That gives us 1.89. So 1.89 here. Or we'll do the other one. 1.47 minus. So let's repeat the first one, be sure. 1.47 plus 1.204 divided by 2.9. The error in that one, the answer is 0.992. Let's correct the mistake for this one. 0.9922, sorry. Why for the other one? 1.47 minus 1.204 divided by 2.9 give us 0.0917. So 0.0917. So there are the two values for S. So let's go up. So have S as either 0.922 or 0.0917. Someone may ask, what if I got a negative answer on one of the S values? Positive or negative, I will discard the negative, because concentration can never be negative and go ahead with the positive. But since the two answers are positive, I will still select one. How do I select one? So I go back to the equation. The concentration at equilibrium for hydrogen gas concentration from the IC table is I think we'll have 2 minus S. That's what we got. No, yeah, we'll have 0.1 minus S. 0.1 minus S. So that's the concentration at equilibrium. And also for iodine, the concentration at equilibrium is also the same, is a 0.5 minus S for iodine from the ICE table. Now if you look at the two values, this 0.9 is more than 0.1. And then 0.9 is also more than 0.5. So the concentration of this will not work. So we're taking our S as this, because this value, if you put it here, you're going to get a negative answer. Please put this one here, also get a negative. So in other words, we're picking S at the smaller value, discarding the bigger value, because the 0.1 is more than 0.0917 and 0.5 is more than this. Should I put this value here, 0.922 here, or they are going to negative answer? And concentration can never be negative. So if I replace S with this, I have 0.1 minus 0.0917. For this one, I have 0.5 minus the same value of S, 0.0917. So when we subtract the first one, 0.1 minus 0.0917. So I'll get 0.0083. So 0.0083 mole per dm cube. Now, if I do the second one, I'll have 0.1 minus, 0.5 minus 0.01917, and that gives us 0.4083. So 0.4083 m. The first one is, let's repeat it. The first one, I got 0.1 minus 0.0917, that is 0.0083. So the concentration of hydrogen at equilibrium is 0.0083, while that of iodine is 0.4083. Then the concentration of hydrogen iodide from our ICE table is 2s, which is 2 times the value of s, which is 0.0917. Multiply them together, I will get 2 times 0.0917, 2 times 0.0917, I'll get 0.1834 mole per dm cube. So these are our final answers. We'll take one more question on calculation of concentration from equilibrium constant. So let's look at the question on the board that shows the decomposition of dinitrogen 4-oxide N2O4 to give us 2 molecules of nitrogen 4-oxide NO2. The equilibrium constant is 1.07 times power minus 7. Question A says, calculate the equilibrium concentration of NO2 in a solution prepared by dissolving 0.20 mole of N2O4 in 400 ml chloroform. Question B says, what would be the percentage decomposition of the original N2O4? Now, let's look at this problem. Let's start with the first one, then go to the second one. You look at the first question, the information in the first question, they give us the number of moles of N2O4. So this is the number of moles of N2O4. Initial mole, they call it I, 0.2 mole. The volume of the solution, chloroform, is 400 ml. 400 ml of chloroform. I will know that volume should be expressed, since we want to calculate concentration, volume should be expressed in liters because concentration is given by unit mole per liter, not mole per milliliter. So convert the volume to liter, divide by 1,000, that will give you 0.4 liters. So we're going to find the initial concentration of the dinitrogen 4-oxide. So that will be mole over volume, which is 0.2 mole all over 0.4 liters. And that will give us 0.50 mole per liter. So that's the first step we have to do to get the initial concentration of the dinitrogen 4-oxide. Having done that, we're now going to prepare our table, our ICE table. ICE, as I said, means initial, change, and equilibrium table. So we have the substances, then the concentration of the reactant. We have only one reactant here, N2O4, and the concentration of the product, NO2. So initial concentration, so for this is what obtained as 0.50 for our calculation. And then initial concentration of the product is 0 because at the beginning of the reaction, no product was formed before the reaction started. So that's why it's 0. So we now get the change in concentration. To get the change in concentration, we refer to the reactions, stoichiometry of reactions. You see that for the balance equation, we have N2O4 giving us 2NO2. 1 mole of this gave us 2 moles of that. If S moles of this decomposes, we're going to have 2S obtained from this side, that is 2 times S. So you see how I did it. So, having done that, I'll now say change concentration of this one will be negative S, then minus S, S amount of this being decomposed, and then 2S being formed on this side. So the equilibrium concentration How do we get it? For the reactant, it will now be 0.5 minus S, the difference. So for the product, it will now be 2S plus 0, which is 2S. Why do we subtract for the reactant? Because the reactant is the initial, the amount you started with. This is the amount that has left the reactant to the product. So what remains at equilibrium now the difference between the two. So having done that, the next thing we'll do is we'll now write the equilibrium constant expression for this reaction, which is going to be Kc equal to the constant of the product raised to the cubic number of moles raised to power 2 over that of the reactant N2O4. So we'll make a substitution and then start solving. We have been told initially in the question that the constant of the equilibrium concentration is 1.07 times power minus 5. So write 1.07 power minus 5 in place of Kc equal to the equilibrium concentration of the nitrogen 4 oxide is 2S. We're going to have 2S all squared all over that of the reactant, which is 0.5 minus S, bracket closes. So making the correct substitution. The next thing, let's write the upper table. We then cross multiply. So we'll now have 1.07 power minus 5 into 0.5 minus S equal to 2S all squared. So you open the bracket, 1.07 power minus 5 times 0.5 we're going to give us a value 5.35 times power minus 6. Good. The 1.07 power minus 5 times S give us 1.05 power minus 5 bracket S equal to, open 2S and 2S give us 4S squared. So we are moving into a quadratic expression. So we're going to transfer everything on the right hand side to the left hand side. So we're going to have 4S squared plus 1.05 power minus 5 into S. This crossing over becomes plus. Minus, this crossing becomes minus 5.35 power minus 6 equal to 0. So we have a quadratic equation to resolve here. So having done that, so the general form is AS squared plus BS plus C equal to 0. So the coefficient A here corresponds to 4, B corresponds to 1.05 power minus 5, and C corresponds to minus 5.35 power minus 6. You see that? So having done that, all we have to do is to write the general formula for the quadratic equation. We now have S equal to minus B plus or minus B squared minus 4AC all over 2A. So to find our S, which is concentration, we now plug in these values into this equation. S becomes minus 1.05, that is minus B, power minus 5, plus or minus B squared, which is minus 1.05 power minus 5, all squared. Then minus 4AC. A is 4 and C is negative 5.35 power minus 6. Everything all over 2A. A, of course, is 4. 2 times 4. So solving this problem out, what then do we have? We're going to have S equal to minus 1.05 power minus 5 plus or minus, we now expand what have inside the bracket, minus 1.05 to the power minus 5 all squared will give us 1.145 to the power minus 10. Then here minus times minus give you plus. 4 times 4 is 16. So 16 times 5.35 to the power minus 6 give us 8.56 to the power minus 5. So you can put this in bracket and this one also in bracket. All over 2a, 2 times 4 is 8. We continue solving. We have minus 1.05 power minus 5 plus or minus. You now add these two values in bracket inside the square root. That gives us 8. That gives us around 8.56 to the power minus 5. So that will still give us approximately 8.56 power minus 5 all over 8. So we move up to solve further. So S now gives us negative 1.05 power minus 5 plus or minus. We take the square root of what is inside the square root sign. That gives us 9.25 power minus 3 all over 8. And since the value of S should be positive, if I perform subtraction, that is 1.05 to the power minus 5 minus this over 8 to give me a negative answer. So I want a positive answer. So I will do the addition. That is minus 1.05 to the power minus 5 plus. So that will get the positive answer plus D divided by 8. So when I do that, the value of S will now become, I'm going to have 0.00914 over 8. The value of S becomes equivalent to 0.00114 mole per dm cube. So that is the value of S, which we are looking for. So I did not perform the minus because S should not be negative. Minus operation, so I use the addition. Then we'll look for the concentration of N2O at equilibrium, NO2 at equilibrium. And from our ICE table, the concentration of NO2 is 2S. So we now have 2 times 0.00114. That gives us 0.00228 mole per dm cube. So go to the second question. So the next question says, what will be the percentage decomposition of original N2O4? So to find the percentage decomposition, we use concentration of the substance at equilibrium all over the initial concentration of the same N2O4 times 100 over 1. So remember that from our A part of the equation, we got our S as 0.00114 mole per dm cube. And then from our ICE table, we say that the concentration of N2O4 at equilibrium is something as S. You go to the table. So that is something at equilibrium equivalent to S, which is 0.00114. And then when we calculate the initial concentration of this substance, N2O5, using mole over volume, we got 0.5 mole per dm cube. So to find the percentage decomposition of this substance, we just make substitution. We now have equilibrium concentration, which is 0.00114 all over the initial concentration, which is 0.50 times 100 over 1. When we solve this, our final answer will now become 0.2 228. So the percentage decomposition of the compound is 0.228%. So having done that, let's look at the calculations involving calculation of equilibrium constant, because all this why we'll be looking at calculation of concentration using a given equilibrium constant. So let's see how we can calculate equilibrium constant from experimental data. So look at the question on the board to show how we can calculate equilibrium constant. Say the dissociation of hydrogen iodide at 490 Kelvin is given by the equation. 2 molecules of iodide giving us 1 molecule of hydrogen and then 1 molecule of iodine gas. If the equilibrium concentration of hydrogen iodide, hydrogen and iodine are 0.2 mole per dn cube, 0.1 and 0.1 mole per dn cube respectively. Calculate the value of K. So here we're giving the equilibrium constant, the equilibrium concentration of hydrogen iodide, sorry. So we can write as HI equilibrium as 0.2. The equilibrium concentration of hydrogen and that of iodine are equal in the equation. The values are given to us as 0.1 each, 0.1 mole per dn cube. So we have to use these values to calculate the equilibrium constant of the reaction. That is a very easy question. To solve this, all we have to do is we'll write the equilibrium constant expression for this reaction, Kc, that becomes concentration of the product raised to the number of moles divided by that of the reactant. Reactant is hydrogen iodide in this case, raised to the number of moles, which is 2. These ones are 1 each. So now these are the concentrations at equilibrium, which is given to you already. So we'll make a substitution. That becomes 0.1 for hydrogen multiplied by 0.1 for iodine all over 0.2 all squared for hydrogen iodide. So when we solve this, the final answer will be equal to 4. So 4 is the equilibrium constant for this reaction. 4 is the answer. So go to the next question. So look at the next question, which involves the decomposition of phosphorus pentachloride to give us phosphorus trichloride and chlorine, all in gaseous phase. Question says phosphorus pentachloride decomposes in the gas phase to chlorine and PCl3. Calculate the equilibrium constant for the reaction at 300 degrees Celsius. If the original pressure of PCl5 before it decomposes, before it dissociates, was 1.50 atmosphere, and the equilibrium pressure of PCl3 and chlorine are 1.3 atmosphere each. So we're going to build a table here to help us solve this problem. So in this question, we're going to build a kind of ICE table. So we have the reactant, PCl5, then the product. So even though in this case, what we are looking for pressure, not actually concentration. So the initial concentration or the initial pressure of the substances, we're told that the original pressure of this compound is 1.5 atmosphere. And this compound is the reactant, 1.5 atmosphere original pressure. So that means the pressure of this substance before the reaction started is 1.5 atmosphere. And that means the pressure of this ones will be 0 each, because at the beginning of the reactions, PCl3 and chlorine were yet to be formed at the beginning of the reaction. Now let's go to the change in pressure, which corresponds to change in concentration. So change in pressure now will now become, let's say the pressure of this one is P mole, producing the ratio is 1:1:1, as we have learned before. P of this and also P of that. So we'll say minus, because this one is losing to produce this and that. So you have plus here and plus here. And in the equation, we now go to the equilibrium pressure. The equation, we're given the equilibrium pressure of the products. The equilibrium pressure of PCl3 and chlorine given to us in the equation as, let get it clear, as 1.34 each. So that means this is 1.34 produced here, 1.34 produced here. So that means the value of this is 1.34, 1.34 produced. So P should be 1.34, but 1.34 plus this will give you the same 1.34. So the value of P is 1.34. So the equilibrium pressure of this particular one, since it's losing, should be 1.5 minus P. So since P is 1.34, it's going to be 1.5 minus 1.34. Since the reactant is given away. So the equilibrium pressure of the reactant, 1.5 minus 1.34 give us 0.16 at the equilibrium pressure for phosphorus pentachloride. So to find the equilibrium constant, we use the formula for equilibrium constant for Kp, which should be the pressure of the product, pressure of PCl3 multiplied by pressure of chlorine all over. So what will substitute these values after writing this? Substitute 1.34 times 1.34 over 0.16 and divide. We have 11.2 atmosphere as our equilibrium pressure. So next, we are trying to predict the effect of pressure on the equilibrium position. And this prediction is based on Le Chatelier's principle, which states that if an external constraint is imposed on the system at equilibrium, the equilibrium position will be readjusted in order to cancel the effect of that constraint. And these constraints include temperature, pressure, and concentration. So let's predict what happens if pressure is increased or pressure is decreased in a reaction at equilibrium. We know that pressure affects a reaction if the reaction contains gases. So if there is no gas in the system, pressure will have no effect on the reaction system. So what happens? If you read what happened above, increase in pressure favors the site of the reaction with a smaller number of gaseous moles. Increase in pressure favors the side of the reaction with a smaller number of gaseous moles. That means decrease in pressure will favor the side of the reaction with a larger number of gaseous moles. Decrease in pressure will favor the side of the equation with a larger number of gaseous moles. So let's take an instance. So let's look at the following questions to show the effect of pressure on equilibrium position. Let's look at the first one. The question says, state the effects of increase and decrease in pressure on the following. To solve the first one, what we'll have to do is, number one, we'll calculate the number of moles of gaseous reactant, total number of moles of gaseous reactant. So, what does it mean? How do we do that? The number of moles of nitrogen is 1 here, and hydrogen is 3. So 3 plus 1 gives us 4. Then for the product, total number of moles of gaseous product is only 2 here. So since we say that increase in pressure will favor the side with a smaller number of gaseous moles. So for this reaction, if you increase pressure, the equilibrium will shift to the right. The right means you get this side is smaller. So this side will favor, you're getting more of the product because this is the left-hand side, this is the right-hand side. So if you increase pressure, the equilibrium position will shift to the right, or you're going to favor the forward reaction, the side that has a smaller number of gaseous moles, or you're going to get more ammonia or more product. Then if you decrease pressure, on the other hand, the side with a larger number of gaseous moles, which is the reactant side, is favored. So if you decrease pressure, the equilibrium will now shift to the left. So you are favoring the left-hand side. You're getting more reactants. and less product. So if you decrease pressure, the side that had larger number of gaseous modes is favored. So you see how it is done. Now let's go to number 2 question. They are up. For number 2, they are all gases. The total number of moles of gaseous reactant is only 2. The total number of moles of gaseous product is 4 here and 1. 4 plus 1, 5. The side that has smaller number of gaseous moles is the reactant side. So if you increase pressure, the side that has smaller moles is favored. So if you increase pressure, the equilibrium will shift to the left. That is, you're getting more of the reactants, or the backward or reverse reaction is favored by increasing pressure because of a smaller number of moles. If you decrease pressure, the side with larger number, that is this product side, is favored. That means you shift equilibrium to the right hand side, favoring the product side. You see that. Then going to number 3. Let's go on. For number 3, the total number of gaseous, remember that this is solid. In pressure, we are concerned with gases. So this is a solid. We don't take this. This is the number of moles of gaseous reactants. So this is not a gas. This is a gas. Steam, 4. Then here, this is solid, S, solid, ignored. And this is a gas, this is G, hydrogen gas, 4. So for this number 3, whether you increase, since the number of moles on both sides are equal, so for number 3, increase or decrease in pressure will have no effect on number 3, no effect on the reaction, because the number of moles on both sides are balanced. So there will be no effect or pressure changes, whether increase or decrease on number 3. Then going to number 4, reaction, you see that in number 4, this is solid, this is solid, this is solid. There are no gas in the system. So whether you increase pressure or you decrease pressure, it will have no effect since there is no gas in the system in number 4. So let's look at the effect of temperature changes. So let's look at the effect of change in temperature or change in temperature on the equilibrium position. On the board, we have for an endothermic reaction. How do you know an endothermic reaction? You look at the change in enthalpy, delta H must be positive. So increase in temperature for endothermic reaction favors the forward reaction. What it means, the equilibrium will shift to the right if you increase the temperature of an endothermic reaction, giving you more products. While decrease in temperature favors the reverse reaction for the same endothermic reaction. How do we explain it in a simpler way? Consider yourself boiling water with a stove, kerosene stove, and you know that you have something to catch up with after boiling the water. You have something to attend to, so you have a place to go to, and perhaps that water, of course, you know, want it to boil faster, and the kerosene stove not giving you the kind of heat that you need, and your friend brings in a gas cylinder filled with gas. So what are you going to do? All you have to do is to transfer the water to the gas and to make it boil faster. So in this situation now, the water is absorbing heat. It's an endothermic process, so it needs more heat to go forward. So that is why if you increase the temperature of endothermic that needs heat, you're going to go forward for the forward reaction. If you decrease the temperature, you can start getting colder in the case of the water, favoring the reverse reaction. And then for an exothermic reaction, the opposite the case. Exothermic reaction are known by having negative heat of reactions. If you increase the temperature for exothermic reaction, it favors the reverse reaction, while if you decrease the temperature, it favors the forward reaction. How do we illustrate this? Think of when you're ironing your clothes with pressing iron. At high temperature, the iron regulates itself and the indicator goes off and the iron cools on its own because it needs to cool for it to go forward. If not, if it continues getting hotter and hotter, either there's going to be a spark in the circuit or you're going to burn your clothes. So exothermic reaction is giving out heat. It does not need more heat. So for you to make exothermic reaction to move forward, you have to decrease the temperature. For you to make it to move backward or reverse, you now increase the temperature. So let's take one or two examples here. So the question says, study the effect of temperature changes on the following reactions. The first one, you have the nitrogen 5 oxide decomposing into nitrogen 4 oxide and oxygen. Let's look at the enthalpy change is positive. That means this reaction is an endothermic reaction. So if you increase temperature, since we see that endothermic reactions require more heat, they absorb heat. If you increase temperature, you're going to favor the forward reaction. The arrow move like this. Forward reaction. That means you're getting more of the product, or they could shift to the right hand side, shift to the right. So because it's an endothermic reaction that requires more heat. If you decrease the temperature, the opposite will take place. Since it needs more heat, if you decrease the temperature, that means you're favoring the reverse reaction. You now shift to the left, getting more reactant. Then for the other one, which is number 2, the reaction is isothermic reaction. It's giving out heat. So it does not need more heat to go forward. So if you increase the temperature of this reaction that giving out heat, you're going to favor the reverse reaction. You're going to shift backward, going backward, because it doesn't need more heat and you're adding more heat to it. Then if you decrease the temperature, it now favors the forward reaction, moving it to the right, getting more product. So that's how you predict the effect of changes on temperature of a reaction at equilibrium. This effect was summarized by a man called a Dutch chemist called Van Hoff in the Van Hoff equation. So we don't have time to go into Van Hoff calculations in this tutorial. So we'll now look at the effect of concentration. So going over to the effect of concentration, we have increase in the concentration of the reactants, or any of the reactants favors the forward reaction, while increase in the concentration of the products or any of the products favors the reverse reaction. So what do you mean by concentration? Concentration implies quantity. Let's look at this example we have on the board. So we have this example. So to increase concentration of the reactant or any of them means to add, we can do it in different ways. We'll add more of the reactants, more of nitrogen or more of hydrogen or more of the two, making this side be larger than this side. That will favor the forward reaction, so we can produce more ammonia and to balance the offset. Then we can still increase the concentration of the reactant by keeping the reactant constant and removing some of the product, making this side having a higher quantity. That will still favor the forward reaction. We can still increase the concentration of the reactant by adding a substance that is not in this reaction. Add a substance that will react with the product to produce one or more of the reactants. Now, how do we increase the concentration of the product? One of the ways to do it is to add more ammonia into the system, and that will favor the backward reaction. Or we keep the ammonia constant and remove some of nitrogen or some of hydrogen. That will still make this one to be in higher amount than favoring the reverse reaction. Or we add a substance that will react with any of the reactants to produce the product. So if you increase the concentration of the reactant, forward reaction is favored. If you increase the concentration of the product, backward reaction is favored. Then these are the 3 things Chatterley had considered in his law: the concentration, pressure, and temperature that can alter the position of a reversible reaction. Then what of catalyst? Does a catalyst have any effect on the reaction at equilibrium? The answer is no. A catalyst has no effect on a reaction that is already at chemical equilibrium. Why? If I add a catalyst, let's say a positive catalyst, you're going to increase the forward reaction and the backward reaction at the same rate. So since you're going to have effect on the two forward and reverse reaction, that means a catalyst has no effect on a reaction at equilibrium. What of a noble gas? Noble gases are said to be inert. Yes. If you add a noble gas to a reaction at equilibrium, it could have effect or it could not have effect depending on the reaction, whether the reaction is performed at constant volume or at constant pressure. So that is it for today. So thank you for your time for this long topic, chemical equilibrium. We have come to the end of this topic. In the next tutorial, we're going to take a look at chemical thermodynamics. So thank you for staying connected. Thank you.